So today's lesson, we're looking at forces in motion still, but this is going to be Newton's first law. So last week was looking at a resultant force, this week's looking at Newton's first law. Now, what do we mean? Well, the objective is to be able to recall exactly what Newton's first law is, and through a number of other video resources, hopefully you'll realise that if an object was stationary, just sat there, and there were no other external forces acting on it, it would remain stationary, or sometimes known as remain at rest. Okay, so that's the first point. So when you look at all forces acting, if there is no resultant force, so this takes you back to last week, if there's no resultant force on the body, then that means that it will just remain stationary or at rest. Or if it was moving, okay, and it had a constant velocity, it would not change its velocity unless an external force acts on it. Okay, so for instance, if you had a car and the car was moving and there was an engine driving force moving it forward, and that was equal to the drag forces, the air resistive forces, the friction between the tyres and the road, if they equaled, there would be a balance force, and so there would be no resultant force. So it would just continue moving at that speed. If you wanted to increase your speed, you would have to increase the driving force. If you wanted to decrease your speed, you'd have to increase the drag forces, maybe by putting your foot on the brake. Okay, so this is what Newton's first law is. I'll just read it out again. So it's just recall Newton's first law, where the resultant force on a body is zero, i.e. the body is moving at a constant velocity or is at rest, and where the resultant force is not zero, the speed or direction of the body will change. Okay, and I'll discuss this with some examples before I show you which additional videos there are to watch on Edpuzzle. So there are a couple more learning objectives to this then. We need to explain that the object moving in a circular orbit at constant speed has a change in velocity. So I'll show what that means in a second. And then also explain that for motion in a circle, there must be a resultant force, known as the centripetal force, that acts towards the centre of the circle. So they're the three main objectives from this week. And the learning outcomes from them, you should be able to describe the effect of a balance force on a moving or stationary object. Okay, so very similar to finding resultant forces on objects from last week. Describe the effect of non-zero resultant forces on moving and stationary objects. So in other words, is it going to change its direction, change the object's velocity? Describe circular motion at constant speed as a changing velocity and hence an acceleration. Describe the force needed to keep an object moving in a circular path. And then give some examples of objects moving in circular paths and the type of centripetal forces involved. Okay, so this is what this week's going to be about. Like I said, with the textbook, with the additional theory I'll go through next, with the additional video resources, hopefully you'll be able to develop your understanding of Newton's first law, and then you can apply that to some multiple choice questions. So I've just discussed some of the learning outcomes, and we'll go through these in more detail now with a bit of theory. The first one said that you would need to describe the effect of balance forces on moving and stationary objects. Okay, so what that means is, for instance, if I have a box on a table, okay, and that box is stationary, there are forces acting on it. You have the weight of the box, but that is balanced with an equal and opposite force, which we could call the normal contact force or support force. I'll put S for support. And so when the weight is equal to the support, there is no resultant force. Okay, if you add that to that, in other words, that minus that, because it's a vector in the opposite direction, you would get zero resultant force. Okay, so we've got balanced force. So that's the resultant F equals 0 newtons. We're not saying that there are no forces acting on this box, we're saying the overall result of the forces is 0. And in that instance, this box will remain stationary, okay? If, however, we apply an external force, let's call this F. These forces are balanced, but now there's an uneven and unbalanced force, a horizontal force, and so this box is going to start moving. Okay, and that brings us on to our second point, describing the effects of a non-zero force. This was for a stationary box that we're getting to move. However, the strange or the conceptually difficult thing to comprehend, to get your head around, is when you actually have an object that is moving at constant velocity. Okay, so for instance the car, if this was actually moving, okay, you would feel that there has to be an unbalanced force. But actually, if the car's engine force was the same size as the drag forces that are trying to hold the car back, so these are the air resistive forces, and we could be thinking about the frictional forces between the tyre and the road. All the forces acting this way are equal to the forces acting that way. So yet again, we have balance forces, okay? And so the resultant force for this this car is 0, okay? And likewise, it will have a weight, but then it will be equally supported by support forces from all 4 tyres, and all the up force equals all the down force. So vertically, the forces are balanced. Horizontally, the forces are balanced. But this was travelling at a constant velocity, so that means it remains moving at that constant velocity. So let's just say this car is travelling at 30 miles per hour. If somebody wanted to increase their speed, they would have to put their foot on the accelerator, so the engine applied a larger force in this direction, and then it would start to gain speed. Or if it wanted to slow down and they put their foot on the brake, the drag forces would increase, or more so the frictional forces between the brakes and the tyres. And so that would then mean that the speed of the car would reduce. Okay, so when you have an unbalanced force, just like here, an unbalanced force would get this moving, an unbalanced force would change its velocity. But before there was an unbalanced force, it was moving at a certain velocity, and it would just remain moving at that velocity unless acted upon by a resultant force. Okay, the third learning outcome today is to talk about things moving in a circle. Okay, so this object is going to move in a circle, and we're talking about a uniform circular motion, meaning that how fast it's moving at any point on its journey around the circle is the same size speed. And remember, speed is scalar quantity, that's just the magnitude part of your velocity. Okay, so it's only how the size of it, how fast you're going. However, if you look, the velocity here is pointing in this direction. So vector quantity, this velocity vector is pointing this way, then it's pointing that way, and it's pointing that way. And as it moves around the circle, it's continually changing its direction. Well, if a vector changes its direction, that means that the actual vector is changing. So the velocity is actually changing. Okay, so when you think about things moving in a circle, the velocity is constantly changing direction. Now, to have it change direction, there needs to be an unbalanced force. There needs to be a resultant force. And if you notice, what's happening is every time the object wants to move this way, it gets pulled towards the center. So there has to be a resultant force acting towards the center, and we call this the centripetal force. And that force causes an acceleration in that direction as well. So actually this thing is accelerating, but changing its direction rather than changing the size of its speed, okay? It maintains the size, and we call that uniform circular motion. And then some examples then. So one of the learning outcomes today was some examples of uniform circular motion. Well, if you've got planet Earth, there's a satellite's orbit, the International Space Station orbit, so orbit is circular motion. It will just continually move around in a circle. The centripetal force is actually the weight of the object being pulled towards the Earth. The reason why it doesn't just hit the Earth is because it's travelling fast enough that every time it gets pulled down a bit, it's now just pointing and heading in this direction, but it never quite reaches the Earth. If it slowed down enough, it would head towards the Earth. Okay, so there's an example of circular motion. Fairground rides, so if you think about a Ferris wheel moving around, or if you think about some sort of roundabout, they're all examples of circular motion. So this will be backed up then with some other lesson resources, some other video resources to help with with the whole of this week's topic, which is Newton's first law of motion.